Hey everybody, I hope everything's going well for you. Um, we're going to move into okay. We've done similar triangles. Okay, we've done similar quadrilaterals. Okay, so keeping in mind that same kind of rule of similarity. Okay, we're going to be using similarity, and this also we're going to include some scales in this. Okay, this is using similarity or indirect measurement. Okay. Well, when we talk about indirect measurement, we did a little bit of this when we did Pythagorean theorem. Okay. And we could still apply that to parts of this with using right triangles, but we're going to do it a little bit different way. We're going to use proportions like what we've been doing. Now, this is one of those lessons, like I said, that comes in handy all the time. In my adult life, I've used this um, indirect measurement many times. Okay, especially when you're doing things um, where you're building things or you're planning things for like a yard or stuff like that. So first of all, remember similar means same shape but not necessarily the same size. Okay, so we're going to first think about what a scale means. Okay, when we talk about a scale, we're talking about a ratio that compares a scaled down, and that can also be or up, measure to an actual measure. Okay, and the easiest example of something like this is if you look at a map, okay, where you see down in the corner, it usually says something like 1 centimeter equals 5 miles, or 1 inch equals 10 miles, or something like that. And you use that to determine how far something is without actually measuring it. You wouldn't actually measure the miles, okay? So you use a ratio, okay? So when we talk about ratios, we're actually talking about proportions, okay? So there's two types that we're going to see. We're going to see some that have a scale, and then we're going to see some that also have an actual similar triangle, like what we've done before, except we're going to use proportions, okay? All right, so let's move into the first example of what we're going to see, okay? These are going to be word problems, but they're not hard, okay? So we have a model house has a scale of 1 inch equals 3 feet. Okay, we're going to keep that same rule that we've been having this whole time in mind, okay? And that's the same shapes. We're going to call this measure on the same levels. So we're going to take what we know here, which is our ratio of 1 inch equals 3 feet. Okay, because we know a model house has a scale of 1 inch equals 3 feet. So for every inch on that model house, that equals 3 feet in real life. Okay, so if the real house is 15 feet tall, then how tall is the model house? Now I'm smart enough to know that you guys can probably figure this out in your heads. However, the important part is that you are understanding the ability to set up a proportion so that you can figure this out. They're not always going to be this simple. Now, if I have inches as my top unit up here, I have to keep inches there. So this second measure, this 15 feet tall is how tall the real house is. Well, feet are on the bottom, aren't they? So this 15 is going to go on the bottom, okay? Because we want to keep the same shape or same measures on the same levels. So this inches is what we're going to find. We're going to call that x, okay? Now, what we have here is a proportion. Okay, we're going to use our cross products to solve for this. So 1 times 15 would be 15. X times 3 would be 3x. Okay, now we're going to go ahead and solve this by dividing each side by 3. And again, I know this was easy. This is a very simple example. Okay, but you would have x equals 5 inches. So on the model that represents the real house, that model is going to be 5 inches tall because the real house is 15 feet tall. Okay, I hope that kind of makes sense to you. I'm going to put an example up here that I want you guys to try, and then we'll move on to the next part. Now on this one, okay, we're going to have to read it pretty carefully, okay, because there's going to be it's a setup a little bit differently, but the same rule applies to this one. Okay, in other words, we're going to have a rule of same level measure on the same measures and same levels on the same side. Okay, same side, same measure. So if we have the top as the two measures we have are centimeters and kilometers. Okay, so let's first write down what we know: a scale of 1 centimeter to 19 kilometers. So we know that Union and Riverside are 171 kilometers from each other. How far apart would the cities be on a map? Okay, so last time we were taking what's on the model to find the real life measurement. This time we're taking the real life measurement to find what's on the model. But we know that we have a scale for every 1 centimeter. In real life, it equals 19 kilometers. Okay, now let's look at the other measurement that we have. We have 171 kilometers. So that, remember, we're going to keep the kilometers on the same level. So that 171 is going to go down here. So what we're trying to find here is going to be the centimeters because we want to know how far apart the cities would be on a map. Okay, so that's going to be where our variable is. Okay, so let's go ahead and look at this. 1 times 171 is 171. X times 19 is 19x. Okay, so I'm okay with you using a calculator on this. On 171, we divide each side by 19, and we get x equals 9 centimeters. Okay, hopefully you got that right. It's really not that difficult once you're able to set this up. Okay, the important part, like I said, is you being able to set this up correctly. The most important thing is keeping the same units on the same levels. Now, I had a question on the last assignment is can we have a variable on the top? You can have a variable on the top or the bottom. It doesn't matter as long as you keep the same units on the same levels. Okay? All right, let's take a look at the next type of problem you're going to see. All right, and this is similar to what we did when we used the Pythagorean theorem, okay, to find missing measures. All right, so on this one, we have a 4-foot tall tent standing next to a statue casts a 2-foot shadow. If the statue casts a shadow that is 7 feet long, then how tall is it? Well, what we have to think about, okay, there's two things we're comparing here. We have a tent and a what? And a statue. Okay, now we know that the tent is 4 feet tall and the statue has a 2-foot shadow. The other measure that we're given here is a what? Statue that is 7 feet. Okay, so when we set this up, we know that first of all that we have to read this carefully. Okay, let's talk about the tent first. Okay, what do we know about the tent? It is 4 feet tall and it is standing next to a statue and it casts a 2-foot shadow. So we know that let's talk about first we're going to have this is the tall or the height and we're going to keep that over the length, okay, of the shadow. Okay, so let's say that if this tent is 4 foot tall and it casts a shadow that is 2 feet, okay, then we're going to compare it to the statue which casts a shadow that is 7 feet long. So that long shadow, is that going to go on the tall? No, we're trying to find how tall is it. So we're going to put the variable up here and we're going to put the length of the shadow down here. Okay, so you can see how we set that up. Okay, we've got the tent here, we've got the shadow here. Okay, now let's go ahead and cross product, multiply these. So 4 times 7 is 28, and then x times 2 is 2x. Divide each side by 2, and we have x equals 14 feet. So we know that statue casts is because it casts a shadow that is 7 feet tall, 7 feet long. Sorry, it is a 14-foot shadow. Make sense? Not too hard. Okay, I have one that I want you guys to try. And I want you to pause this and see if you set it up. Now, if you need to go back and rewind and watch that last example we did, okay, you can. And again, there's with these types, with the indirect measure, not the scale, but with these kind of things, it's actually easy to. You can set them up different ways. Okay, but if we think of the fact that we had a shadow and the length, okay, we can do tall over length. I think that's the easiest way to attack this kind of a problem. So we'll do tall over length or height, whatever you want to call it. Okay. All right. So let's see if you can set this up. Go ahead and pause the video and see if you can set this one up correctly. All right. So we know we're talking about a giraffe that is 8 feet tall and has a shadow that is 20 feet long. Okay. So the height, we're going to put 8 feet over 20 feet. Because again, we're talking about height over length. Now, equals, we're going to find the height of a cardboard box that casts a shadow that is 5 feet. Okay. So again, that shadow, does that represent the tallness? No, that's the length because this says find the height, which is the same as the tall. Okay, so we know our variable is going to go up here, and that 5 is going to go on the bottom because that's how long the shadow is. Okay, let's find our cross products here. 8 times 5, 40, and x times 20, 20x. Divide each side by 20, and we have x equals 2 feet. So we know that the height of that box that's casting a 5 foot shadow is 2 feet. I hope all of this makes sense, guys. It's actually very useful. Okay. So if you need to rewatch this a few times, please do so. And we will talk to you tomorrow. I hope you guys have a blessed and awesome day. Talk to you soon.